Hello there. In this video we're going to download Visual Studio with the C++ compiler. So this is the URL that you need to go to, visualstudiomicrosoft.com/downloads. It should look like this, although it may look quite different if Microsoft change it again, which they have done since the last time I recorded this video. If you're not a Windows user, you might be interested in Visual Studio Code. This works on Mac and Linux as well as Windows. This is just the editor part of Visual Studio, so you can get this to work with your compiler if you've got G++ or possibly CLang, or maybe even min.gw on Windows from the last video. So you can just download this and use it with your compiler as a simple low overhead environment. Talking of overheads, Visual Studio is pretty big. It's a download of 1.6 gigabytes. It takes about half an hour on my broadband connection. So if your connection is not up to speed, this may not be the right solution for you, I'm afraid. The version we want to download is this one, Community, free for students, open source contributors and individuals. If you're doing commercial work or working for a business, then you need one of these, which are not free of charge and you have to pay for them. So let's start downloading this one. So first of all, we need to download and save this file. You can save that anywhere on your system if you like. If you can't think of a suitable place, you could use the desktop. So we'll save that. This page is very busy, so we'll go back to the previous one. Now we need to run this executable. So we get the usual Microsoft security warning. Do you trust Microsoft Corporation? Well, that's a big question, but we'll assume the answer is yes. So let's click on Run. So this is just a preliminary bit of configuration. So click on Continue here. You can read about this if you're interested. Fortunately, I downloaded this earlier, so it seems to have cached that. If you haven't already got it, it may take about 5 minutes for this stage. Now it's about to go on to the next stage. So this is just the installer program for Visual C++. Now we're actually going to download Visual Studio. We have various options here. There's different things including Python, and here's something else. There it is. There's Python environment, which may be of interest, but we're doing a C++ course, so let's download this one, desktop development with C++. If there's anything else you want to download, you can check those as well. It won't cause any problems, or it shouldn't as far as I know. So then we can click on Install. It says that if you have a slow download connection, you can have the option to download everything first and then install, as opposed to this one which downloads and installs at the same time. I'm not quite sure what the internet connection speed has to do with that, but I've got a supposedly fast connection, so let's go with this one. Install. While the Visual Studio is installing, we'd like to ask you some questions. Not now, thank you. If you like taking surveys, you can answer this. If you don't bother. Now this is going to do a big download. I don't think there's much educational value in making you sit and watch the download bar go from the left to the right, so I'm going to skip over some of this and catch up at the end of the download. Right, we're getting towards the end of the download and installation now. I've noticed actually I only have 940 megabytes to download. I think I may have partially installed it before. I also made the mistake of pressing the pause button, and then I couldn't find a way to unpause it, so that's why I ended up with a partial installation. So we've got this start after installation checked here, so presumably it's going to roar into life as soon as it completes this stage. So 293 packages out of 301. Just another 13 megabytes to go, so that's the download stage finished. Right, so here we go. Let's see what happens next. Right, it's actually started Visual Studio now, but it's hiding it in the background, so let's bring it to the foreground. It's found some old code that I've got. So let's create a new project. Actually, let's continue without doing anything. Okay, so we now have Visual Studio. We can play around with C++. I'll save that for the next video, in fact, because I think this is probably enough for one video. So I'll see you next time, and meanwhile, keep coding. Hello there. In this video, we're going to find out how to create a C++ program using Visual Studio 2019. When you start up Visual Studio, you should see something that looks like this. You may get prompted for an account, and if you have an account with Microsoft, you can enter your details. If you don't have an account with Microsoft, they'll give you a link and you can click that and go off and set it up. You don't have to create an email address with Microsoft, although they may try and make you think that you have to. You can use any email address that you have. Normally, I'd recommend starting with empty project, so you can add just the code that you want in your program and not any extra stuff that Microsoft put in there. But as we're trying out the compiler, we'll go for console app. If you don't see any C++ in there, it probably means that the C++ hasn't been installed. So you can scroll down to the bottom of the screen, click on Install More Tools and Features, and then eventually the installer will open again and give you some options of things to install. So this is the one that we need. So we need the workload for desktop development with C++. On my installer, it's already been selected because I installed it. If you don't have this, then you need to select it. You can select other ones if you want to, but with this course you'll only need this one, and then you can go away and install it. Okay, I'll just close that. So we're going to create a console app. Then we click on Next. And try to think of a better name for the project than that. Let's call it Hello. In fact, I've already got a Hello project, so this is going to be Hello 2. Then we can just accept the rest of the defaults, unless you have a reason not to. Let's create that. So this is the actual integrated development environment. This window here has the source code. These are instructions in a form that humans can, in theory, understand. This is going to be processed by the compiler and converted into instructions that the computer can understand. We have some other windows here. This one lists everything that's in the project. If we click on the source files, we should see, yes, we've got hello2.cpp. So it's created a file called hello2.cpp for this project. This window here is where the communication from the compiler will appear when it's creating the program. So another window here, I'm not quite sure what this does. I've never bothered to investigate it. And as you'd expect in a Windows application, there's all the menus with various things up here. So don't worry too much about what this does. This is the actual bit that the compiler will process. The rest of this is just comments which are ignored. So this is useful to run the program. Control plus F5 or debug start without debugging. So let's try doing that. Debug, start without debugging. So you can see we're getting some output here from the compilation process. Right, so this is another thing that's new in Visual Studio 2019. We get this noise which confuses the issue. I'll just close the window and get rid of that actually. So debug, options, then general. Then go down to the bottom and select this one, automatically close the console when debugging stops. That does actually keep the console open, but it removes that error message. So that's a very badly worded option. Anyway, enough ranting, let's get on with it. Debug starts without debugging. So there we are. So we get hello world. So this program will print out hello world if everything works properly. So this tests that the compiler is working. It also tests that we can do input output. So that's quite a thorough test of the features. Then this extra bit of code here has been added to the program. Press any key to continue. If we create console applications every time, we'll get this. So this means that the window is going to stay open and it'll give us a chance to see the output from our program. So going to press a key to continue, which will close that. Okay, so that's basically it. Welcome to the world of C++ programming, and keep coding. Hello, in this video we're going to look at the Hello World program. So this is almost a kind of in-joke really. It goes back to the 1970s when two of the people who developed the C programming language wrote a book, and the first example program in that book was some code that printed the words Hello World on the screen. You can imagine this is maybe a monster coming to life, or maybe the start of something new and exciting. The reason why they chose this particular program is really as a check to make sure that the compiler was installed correctly. So it checks that the standard include headers have been installed and the compiler can find them and read them. It checks that the standard library files have been installed and can be found and read by the compiler. And then it checks that the compiler can produce a valid executable. That's all quite a lot for a simple program. This was picked up by other people. Eventually every book or course that teaches C had a Hello World program as the first example. And then when C++ came along, they were all old school C programmers, so they carried that on as well, and people have been doing it ever since. So we're going to respect this ancient tradition, and this Hello World program is going to be our first program in C++. Unless of course you programmed in C++ before, in which case it won't be. So the source code for this program is shown in the next slide. It's just a few lines that you need to copy out. In case you don't pause the video quickly enough, or if you want to have a copy for your own records, I've uploaded the slides for this video and put them as a resource for this lecture. And there's also some exercises with suggesting ways you can tamper with the program and see how it breaks. So have a look at those. In fact, for every lecture that I post related to C++, there is a resource which is a set of slides with exercises in. So these will give you some ideas for experimenting and changing things around. So if you do those will be a very useful exercise and practice in writing C++. So what you do with this is you create a project if you have an IDE, or you just open a file if you have a command line editor. Then you copy this code into the file, you save it as hello-world.cpp or some similarly suitable name. Then you build it or compile it. Then you run the program, and with any luck it should print out the words Hello World on the screen. Now make sure that you type it in exactly as shown, because as we discussed in the previous video, compilers are very pedantic, and if you make just a small mistake, leaving off one character maybe, it'll throw a fit and you won't get a binary to run. So do try and type it in very accurately. Okay then, so here it is, and I'll leave you to copy that out and get it running, and good luck with that, and I'll see you next time. Hello, so we're going to start off by looking at how a computer works. Obviously modern computers are very sophisticated and we won't be able to go into a lot of detail, but we'll just have a quick overview which will give us some useful information that will help us when we're writing computer programs. So here, very simplistically, is what a modern desktop computer looks like. So we have the CPU, the central processing unit, which is the heart of the computer. This is where all the bit crunching goes on, and it also sends out commands to the other parts of the computer. It can also receive commands which are called programs. So a program is basically a set of commands to the CPU to do various things, and this can result in the CPU sending off commands to other parts of the computer to do things, and them sending back data, and so on. So main memory, also known as RAM, is used for temporarily storing data. It's also used for storing programs which are being run on the computer. Secondary storage is typically a hard disk or some other kind of permanent storage device. This is where all the data on the computer lives when it's not in use. And we also have some facilities which allow the user to communicate with the computer. I mean, typically you'd get a keyboard, a mouse, and a display of some sort. The CPU controls the computer and coordinates the other components. This is done by sending and receiving electrical signals which represent commands and data. So for example, we have a program which consists of commands. These are fed into the CPU, and the CPU might send some other commands off to a hard disk drive to get some data, and the disk drive sends back some data, and this is all done using electronics. Main memory is used for temporarily holding programs and data while they're being used by the CPU. Secondary storage is where all the data on the computer is held permanently, and the console is the collective name for input and output devices. It's where the user interacts with the computer. So this is what a RAM module looks like. You may have just one of these in your computer, or maybe 2 or 3 of them. This integrated circuit here is the important bit. So this contains lots and lots of memory cells. Each of these memory cells contains a single number. There's a blurry thing here which is a controller chip which controls the flow of data into and out of these integrated circuits. And there's some connector pins here which are used to communicate with the rest of the computer. So for example, we could get an electrical signal coming in here saying fetch some memory. The controller will work out which integrated circuit it needs to go to, so it could go to here and get some data from a memory cell and then send it back through the connector pins. So data is stored in memory cells as a binary number. So that means numbers whose digits can either be 0 or 1. RAM is short for random access memory, which means we can directly access any memory cell. The opposite of random access is sequential access, which means you have to start at the first memory cell and go through each one in turn until you get to the one that you want. So obviously random access, where you can jump straight to the memory cell you want, is going to be much faster. Each of these memory cells has an address, so you can think of RAM as being rather like a very long street, and each of the houses in this street is a memory cell which has one occupant, which is a binary number. So to get to a particular item of data, you look up the address, you go to that particular address, and then you can access the data which lives in that memory cell. An important point about RAM is that it's volatile, which means that when you switch the power off, all the data disappears. And the other side of that is when the computer is switched on, there isn't going to be any useful data in RAM. So basically you can't assume that a memory cell contains any useful data unless you know that you put it there yourself. Okay, so this is what a hard disk drive on a desktop computer looks like. So it's just a metal box from the outside. If you open it up, which I don't recommend because it won't work again and you've voided your warranty, this is what it looks like. So we have a disk here which spins around very rapidly, like an old-fashioned record player. There's an arm here which goes back and forwards across the disk, like the arm on a record player. and it reads data off the disk or writes data onto the disk depending on what it's required to do. In the top half of the box we've got all these impressive looking circuitry, and we've also got connector pins here, so this can communicate with the rest of the computer. So we can get commands coming in here to fetch some data, then the arm will go to the relevant bit of the disk, it'll read the data off and send it back. Okay, so that's an example of secondary storage, a hard disk drive. We can also have a more modern thing called an SSD, a solid state drive, which functions pretty much like a hard disk, but it's all electronics inside, so there are no moving parts. We can also have USB sticks, these little things you can plug into the computer for moving data around or installing programs, and an SD memory card, so this is the little card inside your camera which is used for storing all your photos. Secondary storage has a rather more elaborate way of organising its data. With RAM we just had a single number and you went to that address and you could get the data. With secondary storage it has something called a file system, and this is used for organising data into folders and files. And each one of these files contains a collection of data which is stored as a sequence of binary numbers. So for example, if you have a photograph, that would be represented as a single file, and the data in that file would be all the information that's needed to recreate the picture. And then that file would have a name which would typically be the number of photos you've taken since you bought the camera. And you could organise these files inside folders, so you could have one folder for each day's photos. So to access data we need to say which drive it's on, which folder it's in, and the name of the file. So for example, if we're looking at a photo on our SD memory card, we need to go to the memory card, go to the folder with today's photos in, and then go for the file which is the third one from today or whatever it is. And if we're really a computer program which is trying to recreate the picture, we need to know which part of the file we're looking at. So as we're retrieving the data to recreate the photo, we need to step through the file and get each bit of data. Secondary storage is permanent, so it stays there if you switch the power off. Unless something catastrophic happens to the disk, if it's physically damaged or something equally drastic, then the data should stay in there forever. Files usually have some meaning and are often structured. So for example, the photograph files, they have a particular format, which means they can be recognised as representing pictures. So software which examines these files can tell straight away that they are representations of a picture, not, for example, a word processing document or a spreadsheet. Input and output devices, I think you're probably all pretty familiar with these. So we have a keyboard, a mouse, the display or monitor or screen or whatever you want to call it. So this is where you can type in data here, you can select things with the mouse, you can highlight them or choose something from a drop-down list, for example. And then on the screen you can see the results of what you're doing, or the computer can ask you for some data which you can enter with using these. So all that's known as the console, so this is where humans interact with the computer. The monitor will display output, so this will enable you to see whatever the computer is doing. And we can issue commands to the computer using the keyboard or the mouse. Okay, so that's it. That's a quick overview of what computers do, and I'll see you in the next lecture. Hello, in this video we're going to look at the function and operation of the CPU. So the CPU is not particularly interesting from the outside. All you can see when it's mounted on the main board is the metal heatsink on top. Underneath there are a huge number of metal pins which may look like a complete jumble, but in fact they are all organised into groups, and each group has a specific purpose. In fact, the connector pins on the CPU are arranged in groups, and each of these groups represents a single binary number. Each pin in a group represents a digit of the number, a single digit. These are binary digits, so they are bits, and they can only have the values 0 or 1. Whether it has the value 0 or 1 depends on the voltage on the pin. So a high voltage, which is usually 5 volts or 3.3 volts, a high voltage corresponds to the value 1, which means that the bit is set. A low voltage, which is usually earth or 0, means that the binary digit has the value 0 and the bit is said to be unset. So these groups of set and unset connector pins correspond to binary numbers. So here we've got a very simplistic CPU. So we've got a group of pins here with voltages on. So this has a high voltage, it's set, that has a low voltage and it's unset. And all these pins together correspond to a binary number. And there's another one down here, so unset, set, set. So we have another binary number on these pins. So this is really the bit where the magic happens, where the electronics and voltages get converted into mathematical concepts like numbers. So these numbers can represent either commands or data. When they represent commands, they're called instructions or codes, and they tell the CPU to do something specific. They can also be data, which is just information that's being used by commands for processing. So for example, we could have a sequence of commands that arrive on the pins and tell the CPU to get some information from RAM, and the number on the data pins would correspond to the address in RAM where the information is kept. So this is a very simplified representation of the structure of a CPU. There's 3 elements: the control unit, the registers, and the ALU, the arithmetic and logic unit. The control unit is the complicated bit really. It supervises the operation of the CPU. A register is an onboard memory cell, so the registers are a group of memory cells which are actually on the same bit of silicon as the CPU. So the advantage of this is that they're very close to the rest of the CPU, and moving data around the chip is much quicker than bringing it in from other parts of the computer. The ALU, the arithmetic and logic unit, it performs basic calculations and comparisons and similar arithmetic and logical operations, as the name suggests. So for example, the control unit could decide that it needs to add together 2 numbers which are in registers. So it'll instruct the ALU to get these 2 numbers, add them together and put the result in one of the registers, or maybe a different one. So these instructions come into the CPU. There's a rhythmic structure, if you like, a kind of pulse, which is known as the cycle. And every cycle, usually the CPU will process one instruction. So for example, if it's fetching some data from RAM, adding it to the value stored in a register, and then storing the result of that sum in RAM, that would take 3 cycles. A modern CPU is amazingly fast. It can perform around 2,000 million cycles in each second. So let's have a look at how the CPU operates. Again, this is very simplified. So at the start of each cycle, the control unit will check for new commands. It'll find that it's got a command, it'll take it apart and work out what it has to do. The control unit could send an instruction to RAM telling it to send data from a certain address into one of the registers. When this data arrives in the register, the control unit instructs the ALU to add it to another number which is already stored in a register. Then when that's done, the control unit will send the result from the register back to the address in RAM. Okay, so the CPU is controlled by a sequence of instructions or codes which arrive on its control pins. These are stored in RAM and sent to the CPU, 1 instruction per cycle. and this sequence of instructions is known as a program. So what happens when a program is run is that it's loaded up into RAM, and then the instructions are sent off to the CPU to be executed. Right, finally the CPU needs to be initialized, as we need to have some way of getting programs into RAM. So what happens is that there's another area of memory which I haven't shown, which is called ROM, or read-only memory. This is a chip which has the instructions burnt into it when it's manufactured, and they can't be changed after that. So these will contain a sequence of instructions which get the CPU started up and initialized. So when the system is switched on, the sequence of instructions is sent from ROM to the CPU, and that will initialize all the other components in the computer. If we have a very simple system such as a washing machine or a gadget that's battery powered, this sequence of instructions completely defines everything that the system can do. So for example, with the washing machine you can set different cycles and turn it on and off, and that's about it. So these instructions are going to control the CPU until the system is switched off. If you have a more complex system like a desktop computer or a smartphone, these ROM instructions will initialize the CPU, and then they'll continue. Typically they'll load a program off the secondary storage, which is called an operating system, and then this operating system, which could be Windows or iOS for example, will carry on running and controlling the CPU, and then this operating system will provide features for individual applications written by programmers to run. Okay, so that's it for this video. I'll see you next time. Hello, and in this video we're going to look at computer operating systems. We mentioned in the previous video that the CPU controls the computer at the hardware level by sending electrical signals which make different parts of the computer do various things. And the operating system, which is loaded up into main memory, controls the CPU at the software level. So the operating system sends a stream of commands to the CPU telling it to, for example, read some data from the keyboard or write some data to a file somewhere on the disk. So as far as human beings are concerned, the operating system provides an interface to the CPU. So for example, if we want to open a file, we can just say to the operating system, please give us this file, and it'll do that. We don't need to issue any commands directly to the CPU. We don't need to know what instructions the CPU uses. We don't need to know what kind of disk drive the file is stored on and what the controller for that uses. So we've just abstracted out really all the details of actually getting the data from the file. Also, we can use the same operating system with different CPUs, and it'll appear the same to the end user. So if we upgrade our CPU or add some more memory, the operating system will still work the same way. So the purpose of an operating system is to coordinate the hardware and manage competing demands. So for example, if we have a computer that's hosting a very busy website with thousands or maybe even millions of users at the same time trying to access data, the job of the operating system is to manage all these different users and make sure they all get handled efficiently, and that the resources of the computer are divided up in the best possible way. The operating system provides many useful features for interactive users and programmers, so as we saw with opening the file, and it provides a consistent environment in which applications or programs can run. So if you can get your program to work on Windows, for example, it should work on any computer which has Windows working on it, regardless of what the actual hardware is. So some examples of operating systems. Desktop computers and laptops usually have one of these: Windows, Microsoft, Mac, OS X, written by Apple, various versions of Unix, and Linux, which is really another version of Unix, although people often seem to differentiate it for some reason. Mobile devices, phones and pads, and iPod. These usually have either iOS, written by Apple, or Google's Android as the operating system. Real-time system, So these could be systems which, for example, control the engine of a ship, or a plant which bottles up fruit juices. Embedded systems, so these are at a very small scale. They may be battery powered or very simple devices. So for example, a microwave oven, or possibly the focusing device on a digital camera. These often have specially written operating systems. There are some commercial operating systems for real-time systems. In fact, I think there are even cut-down versions of Windows and Unix and Linux for these. For embedded systems, these are often customized. The manufacturer of the CPU often writes a very basic operating system which doesn't really do very much, just the bare minimum for the device to work. Or if it's a really, really simple device, it might not even have an operating system at all, just some code that's stored in ROM. Okay, so the operating system has what's called a kernel. This consists of a clump of CPU instructions, if you like, which are loaded up into main memory and run when the computer is switched on, and continue to execute until it's shut down. So these interact directly with the CPU. They manage the CPU, so they decide how much time the CPU is going to spend processing different applications or different users. And they try to make sure that the CPU spends as much of its time as possible doing useful work. I remember reading about one operating system that was written in the 1970s by a university, and it's actually spent more than 50% of its time working out what it was going to do next. So less than half the actual resources of the computer were available to doing any work, and it spent most of the time managing itself. That's obviously not a very efficient operating system. Modern ones are a lot better than that, I can assure you. Okay, so the tasks performed by the operating system. So it manages the CPU, it launches programs, so every time you double click on an application or tap something on your phone or type in a command in a terminal, the operating system will launch up this program. The operating system manages processes. A process is just one instance of a program that's running. The operating system manages memory, so RAM divides up how it's used. It manages the devices, so secondary storage and console are acting under the supervision of the operating system. So these are controlled directly by the CPU, but it's all supervised by the operating system. It provides facilities for applications and for end users. Okay, so that's it for this video. I'll see you next time. Thank you for joining me. Hello, and in this video we're going to talk about operating system interfaces. So we've already seen that the CPU is controlled by the operating system. This is software which is loaded up when the computer starts and sends a constant stream of instructions and data to the CPU. So this drives the CPU in effect. On a modern computer, most of the components are in effect miniature computers themselves. So they have a little controller chip which manages the device. So for example, on the hard disk drive, it'll have a controller chip which decides when to spin the disk up, when to move the arm around, where to move it to, and so on. So these controllers need to have software inside the operating system to drive them, and this is known as a device driver. So each device on the computer has its own specialized bit of software which is particular to that component. The device driver will send commands and data for the component via the CPU, and then the controller can send data back from the device to the CPU to the device driver. Usually the device driver will have an area of memory which it can use for storing data. So there are two reasons for this. The first one is that if the data arrives from the device and the operating system isn't able to handle it because it's busy, it's a multi-user, multitasking system, and it can't do everything at once. So the data will have to wait its turn. So this allows the data to be kept somewhere until the system is ready to handle it. And it goes the other way as well. If the operating system sends some data to a device and the device is busy doing something else, then it'll get queued up in the device driver. The other reason for doing this is buffering. read and write operations on a device are very slow by CPU standards. It could easily take 500 or 1000 CPU cycles for an item of data to be read or written. So in the grand scheme of things, it doesn't really make any difference how big the data is. Writing 1 kilobyte takes about the same time as writing 1 megabyte. So this means you really want to have as few read-write operations as possible. So for example, if you have 10 bits of data which are each 1 kilobyte, if you write them separately, that's 10 operations. If you store them up and write them as a single 10K block, that's just 1 operation. So that's going to be 10 times faster roughly. So if you can take small blocks of data and build them up into one big block, that will make things a lot faster. And that's known as buffering. So basically what the device does is it collects small amounts of data and waits until it has a big enough block and sends it off. So that'll usually be when it has the maximum amount of data that the device can handle in one go. So the advantage of using device drivers are abstraction really. The operating system doesn't need to know any details about the hardware. I mean, this is the rest of the operating system. Obviously the device driver knows all this. So it'll know what kind of controller chip it has, what make, what brand, what instruction set it uses, all the details. And also the device driver abstracts away the details of how to operate the device from programmers. So programmers can write application code without needing to know anything about how the device works. So if you want to save some data, you can just open a file and send the data off. And that's it. You don't need to know what kind of device it's being stored on. Having a specific bit of software for each device makes it easier to optimize the way that the operating system interacts with that device. Graphics cards are a good example of that. These are the circuits that determine how the display appears. With modern graphics cards, there are lots of options which you can tweak around, so it's useful to be able to get the best possible performance from it. And also using device drivers enables buffering and queuing, as we've just seen. Okay, so that's how operating systems interface to hardware. They also need to interface to human beings. So the first stage in doing that is something called an application program interface. These are basically a set of functions which programmers can call. So when programmers are writing an application, they can just use a feature of the computer without needing to know any details about it. So as we said, you can just open a file and not know where it's stored. Another example, displaying something on the console, you just tell the operating system which character you want to display, where you want it to appear, and up it pops. You don't need to know anything about the actual plumbing that achieves this. And also, as well as programmers, the computer needs to interface to end users. End users need to be able to enter input and give commands to the computer. They also need to be able to see the results of their commands. Sometimes the computer needs to ask them for instructions or to make a decision, or sometimes it might display some information about how to use a program. So computers provide some kind of interface where the user can interact. On older computers, this is just a terminal where you can type in commands in text mode and view the results in text mode. On modern computers, these are generally graphical user interfaces, so these have lots of nice pretty things to look at and click on with your mouse. These are implemented as software which is known as a display manager. So this is an application which runs on top of the operating system. So this uses the application program interface to actually interact with the computer. So when you click something on your graphical user interface to start up an application, that's an application which is running inside the display manager. The display manager is running on top of the operating system. The operating system has a kernel which controls the CPU and device drivers which control the devices which are attached to the computer. So we have all these layers which we're using. We're sitting right at the top of these layers, but we're not aware of these at all. Okay, so that's the operating system interfaces. I'll see you next time. Hello, and in this video we're going to talk about programs and memory. So let's first talk about applications. So when you double click on an icon on your computer and things start happening, that's an application. So this could be something like an email reader, a spreadsheet program, or a picture viewer. There are also some applications which are started up automatically by the operating system. So these could be, for example, the software that makes the internet connection or some antivirus software. Applications are what's known as computer programs. So this is basically a load of instructions stored in files in a special format. So this program is about writing computer programs. So let's try and learn a bit more about how they work. A computer program consists of a sequence of bytes, binary numbers, which represent CPU instructions. So these numbers are going to be converted into electrical signals inside the CPU, and that'll make things happen, we hope. So when an application starts up, first of all, the file containing the program is loaded up into RAM by the operating system. The operating system then makes the CPU perform the instructions in the program under the supervision of the operating system, and that's known as running the program. So let's look at this in a little bit more detail. So when we double click on an icon or type the name of a program at a command line, that sends a request to the operating system to launch the program. And one of the things that the operating system does is create a new process. A process is basically the running program as seen by the operating system, or OS for short. The process contains various items of information that the operating system needs to manage the process. So these include things like an identifier. The reason for the identifier is that we can have several different instances of the same program running at the same time if we have a multitasking operating system. So the operating system needs to be able to distinguish between these, and there is a number called a process ID which is typically allocated to each process. There's also a priority level. So this basically means how important this process is in terms of getting a share of the computer's resources. And then the operating system will schedule the process to run, which means that it reserves some time on the CPU when it can execute and do its thing. As we said, modern computers are multitasking. They can have many processes running at the same time. The operating system is responsible for controlling and coordinating all these different processes and making sure each one gets fair access to the system's resources. And the priority level is used for this. So processes with a high priority are given more time on the CPU than processes with a low priority, as you might expect. But there is a kind of equalizing effect built into it, because as a process spends more time on the CPU, its priority level gets gradually reduced, so a process which tries to monopolize the CPU won't be able to. Another thing that the operating system does when it starts up the program is to allocate memory to store the program code. This program code has to be read into RAM, so the operating system will need to reserve some memory for that. It'll also need to allocate memory that the program might use while it's running. Why do programs need data when they're running? Well, there's basically two important cases. The first one is for storing important data which could last for quite a long time, maybe even the duration of the entire program. So for example, if you're viewing a picture, the data that makes up the picture needs to stick around for quite a long time. And the other case is when we have temporary data. For example, if we're doing a calculation and we have some results which we do another calculation with and then throw those away. So computers tend to throw out quite a lot of information which is only used for a very short period and then disappears again. So for example, in a picture viewer, if we rotate the picture perhaps through 90 degrees, then there's going to be some calculations done. There's going to be some values which are calculated during that process and then not used again. So that's temporary data. So these two types of cases are associated with different types of memory. I mean, it's all RAM underneath, but it's the way that it's managed that's different. The important long-term data is stored in heap memory, and temporary data is stored in the stack memory. Operating systems manage the computer's resources, and one of the things they have to manage is the way that the main memory is used. So operating systems divide up the available RAM between different processes. They try and ensure that as much of the RAM as possible is given to processes which are performing useful work. It tries to provide some kind of security between processes. So each process has its own area of memory, and the operating system prevents processes from interfering with each other's memory areas. And the operating system will also terminate processes that try to use up too much memory, or if they do other dubious things that compromise the integrity of the system. In reality, all these bits of memory for processes are going to be allocated all over the place. The operating system will allocate whatever memory comes to hand, really. So it's quite possible that the memory for one process could be split across different parts of RAM, with memory from different processes in between it. In the old days, programmers actually had to be very careful about how they used memory and be very aware of this sort of thing. But fortunately, nowadays we have virtual memory, and we can basically pretend that we have a huge amount of memory we can just use as we wish. The operating system will present us with this big block of memory, and it'll all just appear to work. In fact, as I say, this memory could be spread all over the actual physical RAM. So this has a big advantage because programmers don't need to do any kind of manual management. It also gives the operating system the opportunity to move around a process's allocated memory, if that makes things more efficient, because the process doesn't actually know where the memory really is. So if it's moved from one part of RAM to another, it'll still appear to be in the same place in the program's virtual memory. And this leads to something called paging. The idea of paging is that RAM is quite a bit faster than physical disk activity. So accessing data from RAM is probably about 10 times faster, maybe even 100 times faster than accessing data from a disk. So if you have too many programs running which are using up too much memory, some of them can be temporarily stored on the disk, and that'll make memory available for processes which are active. So for example, if you've opened up your email reader and then you go off and work on a spreadsheet for 20 minutes, your email reader isn't actually doing anything. So if you're doing a very intensive calculation on the spreadsheet that needs a lot more memory, then the email reader could be paged out for a bit. And then when an email comes in, it can be read back into memory. Okay, so that's it for this lecture. I'll see you next time. Hello, and in this video we're going to discuss what is C++. Well, the short answer is that C++ is a computer programming language. Well, what kind of computer programming language is C++? It was designed for writing large, complex applications which need high performance, and these tend to be a bit rather conflicting requirements. Normally when you have a large, complex program, it needs a lot of management and scaffolding and boilerplate to hold it together, and that tends to slow things down. Usually programs which have high performance tend to be sort of small and very well focused. C++ is widely used in what are called embedded systems, so these are things like TV controllers, microwave ovens and so on. They'll probably have very little in the way of memory, so you have to be very efficient about the use of memory. And for devices which are battery powered, they also need to be very energy efficient. So if you're constantly bashing the CPU, that's going to run the battery down pretty quickly. So you need to be pretty careful about how much computation power you use as well. So C++ gives you the best of both worlds in some ways. It supports high-level abstractions such as object orientation, which is one way for organising large, complex programs. But it still gives programmers access to all the low-level features. So for example, if you need to write your own memory manager, you can do that in C++ which you can't do in many other languages, many other high-level languages anyway. And C++ allows access to all the operating system features, so nothing's hidden from you. In fact, you can even write your own operating system in C++. That's how low-level it gets. Static typing in C++, this is one of the most distinctive features about C++. Most high-level languages use something called dynamic typing, which means very simply that you write your code and then run it, and if something goes wrong you try to sort it out while the program's running. With C++, you write your code, then you compile it, which does a lot of checking on the code, and only if it gets through this checking stage can you actually run the program. So the idea is that you try and catch as many errors as possible before you actually start to run the program. The benefit of this is that you don't need to put lots of code in your program to check for errors when it runs, and you also don't need to put lots of code in to sort out the errors when they happen, because the compiler has already forced you to stop them happening. That's the theory anyway. The compiler checks for the correct use of types. These means basically if you're trying to use one kind of data in a situation where another type of data is required. For example, if you have a duck and you try to give it a duct, then the compiler will stop you from doing that. In a dynamic typing language, the program will run and then you'll get a runtime error, and then you have to try and sort out what happens. So the compiler has lots of information which it collects about the code while it's checking all this type information and the other things that it checks. And this means it has a very good knowledge of how the code works. And this means it's very good at optimizing the code. So this means that C++ programs should be better optimized than in other languages. So I know this all sounds a bit esoteric, so here's a more of a down-to-earth example of static typing and dynamic typing. So when you get a compile time error, that's static typing, and when you get a dynamic runtime error, that's dynamic typing. So here you can see someone who's been having a very good time, and he wants to go for a drive in his car, which is probably not a good idea. With static typing, someone comes along and checks whether he's in a suitable condition to drive, and they say, you're not able to drive, stop, you can't do it. With dynamic typing, runtime errors, he's allowed to go off and drive his car, and then the inevitable accident happens. You can see there's a bit of the road falling into the river, and now he's got to sort out the problem. That's just a cartoon I found on the internet, by the way. I hope it brings the concept home. So C++ supports several different programming styles. A lot of languages only support one. C++ supports the procedural programming style. I realise these might sound a bit difficult to understand if you've not done much programming yourself, but if you haven't, don't worry too much about it. This is really just a list of reasons why C++ is so great. So procedural programming really means that the programmer is God. You anticipate the exact course of the program. It starts at the beginning and carries on to the end. So this is often used for data processing programs where you load in some data, process it, and print out a report or something like that, and then you stop. Object-oriented programming is where you have data that manages itself. The best way to think of that is something like a simulation or game where you have various participants, such as players in the game or molecules in a chemical reaction that move around and bounce into other molecules or the walls of the container. The participants in the game, they can run around and shoot each other and crash into the walls and so on. And with an object-oriented program, you basically set up all these players and then let them go off and do their own thing. Functional programming is where the data is fixed as much as possible. You try to avoid making any changes to the data when you're processing it. Again, this sounds a bit abstract. The main advantage of this is for what's called concurrent programming, where you have several programs or several threads within a program which are working on the same data at the same time. One of the big problems in computer programming is when you have different processes trying to work on the same data at the same time. If one of them updates the data when the other one is not expecting it, you can get all sorts of problems. So obviously, if you can avoid changing data, then it makes it a bit easier to manage all that. Then finally, generic programming, which is another completely different way of looking at it. You try and write programs which can work with any kind of data. So this is more of an algorithmic type of approach. For example, if you're sorting objects, it could be putting books into alphabetical order or arranging children in order of height. The actual procedure for sorting doesn't really depend on the thing that you're trying to sort. So if you're putting children into order or books into order, you would arrange them in the same way. What is C++ used for? I mean, you can use it for almost any kind of programming really, but these are the most popular areas. So the first one is games programming, which are usually pretty large programs. Games programmers want to have the most impressive looking games possible, and they want to have the most realistic action. And they also want to be very efficient as well, so the games run smoothly. You don't want to sort of have the game stopping for a couple of seconds while the computer catches up with the action. So C++ is a very popular choice for games. Financial services, so this is banks and other organisations which deal with money. They often deal with very large amounts of data, and they usually need to get it transferred from one place to the other very quickly. I actually came across a good example of that when I was working for a bank. They employed a group of programmers to write the overnight processing. So this goes through all the accounts and make sure everything's settled up and all the money's been placed in the right accounts and so on. And they actually managed to write a program which took more than 24 hours to run. So if you think about it, you run this program every day and it takes 24 hours, more than 24 hours, so you get further and further behind as you go on. And I don't think they stayed with the company very long. Maybe they should have used C++. And also for trading systems. So these are systems which buy and sell things in the markets, and they need to react very quickly to events. So if there's some news item that comes out, or there's a price movement that creates a signal to put on a trade, they need to be able to react to this information and put the trade on as quickly as possible. Embedded systems, we've touched on these briefly before. These are systems which don't have very much in the way of resources, but they need to manage them very efficiently. And an interesting one is developing other programming languages. So often programming languages tend to be large and complicated. People who design them want to have lots of features and make them easy to use. And obviously you want to make them nice and efficient. Again, you don't want to hang around while the language sort of churns through your source code and ponders about what to do next. You want a nice, snappy runtime. So C++ is good for that as well. So here are examples of some programs in C++ that you will have heard of. Web browsers, Internet Explorer, Safari, Firefox, not Firefox, I don't know why I said that. Office software, so these are word processors, spreadsheets, presentations and so on. Website backends, all these famous websites and social media companies that you deal with. Most of them have got C++ running in the background somewhere behind the interface. So digging out user data, finding out things, processing transactions, moving your money around. And compilers and programming tools. As I said, C++ is good for writing programming languages and things that work with languages. Okay, so C++ is really great, and I'm sure you're really excited about it, but I have to be fair and give you the downsides as well. C++ is very large and very complicated, but fortunately you don't need to know all of it, but it does have the characteristic that anything that anyone can think of, there's always some way in the language that supports it. So there's all sorts of obscure features, and even lots of experts don't know the full language. There's a popular saying that everyone only uses 20% of C++ because that's usually enough to write whatever you need. But everyone uses a different 20%. So if you did sort of try and cut C++ plus down to the 20% of useful stuff, there'd be lots of people who'd want an extra feature, and if you added up all the extra features that people want, it would come up to the whole of C++. C++ is very permissive. It allows you to do all sorts of dubious things. Because you do have low-level access, it does allow you to write bad code, and it also allows you to write dangerous code which interferes with the machinery or memory. If you've heard about hacker exploits, these are the kind of things that I'm talking about. Obviously we want to try and avoid those. We don't want people hacking into our code. The way that C++ has been designed is very, shall we say, idiosyncratic. It's been built up over the years. It started off with C, and then they added lots of features, and they kept on adding features. And being backwards compatible is very important. You can still compile C programs with a C++ compiler, but trying to squeeze all this in and not break anything has made it very complicated. C++ tends to have a lot of counterintuitive features. There are lots of things which don't work the way you would expect them to, and often when you do something in C++, it doesn't work the way that you think it would. So C++ requires highly skilled developers. I think C++ probably requires more thinking than any other language that I know of. So in that respect it is more difficult than other languages, but it's also very powerful and easier to do things that you can't do in other languages, so in some ways it is more powerful. But anyway, you do require developers who are very familiar with all these complications and can work with them and write code that works. So these people are highly skilled, so they're expensive to employ. Because writing a C++ program involves doing lots of compiler checking and then fixing all the errors when they appear, it means it takes a long time to write C++ code. The advantage is that it runs quicker when you do actually get it there. So because of all this, expensive developers and a long time to write the program, it means that the production costs for C++ programs are pretty high. So that's really why C++ never caught on as a general purpose programming language. It's normally used where people really want efficient code and they're willing to pay for it. Okay, so again, in the interest of being fair, let's have a look at some of the alternatives to C++. So Java is an object-oriented language. It's interpreted, which means it does dynamic typing with runtime checking. I mean, there may be some Java experts who might argue with that, but I'm just sort of generally being very sort of simplistic here. So Java was designed to be a nicer version of C and C++ really. The standard library that comes with it is probably a lot more powerful than the C++ one and easier to use. And Java is generally easier to learn at the beginning. It gets more difficult when you want to do more difficult things. Difficult things are probably a bit easier to do in C++. But if you do want to learn a language and you're not really sure which one to do, then Java is a pretty safe bet. C# is really Microsoft's attempt to copy Java without looking as though they're copying Java, and don't tell them I said that. So again, it's interpreted, which means it's dynamically typed with runtime checking, and it's an object-oriented language. It's really, if you're interested in the Microsoft world, it works very well with Microsoft's own other products. One thing it is very good for actually is if you want to write programs where users enter data into a form and then you process the form. That's something that C# is strong in. Then we have C, which is the language that C++ derived from. It's also compiled and it supports procedural programming. You can hack in object-oriented programming, but it's a little bit ugly, and getting functional or generic is even harder. So it's a much simpler language than C++ because it doesn't have all the complications that C++ added. On the other hand, it doesn't have all the nice features that C++ added, so you can't, if you want to use those, you have to write them yourselves. JavaScript, again, another interpreted object-oriented language. It was originally written for web browsers, so you could have little flashing text and animated text and whatever, but it's grown a lot since then. And also you can write web servers which use Java. So the advantage of working in JavaScript is you can have code which works on both web servers and web browsers. So if you're doing web-related work, you only really need to learn one language. Incidentally, one thing about Java is there are web servers which are written in Java, so you can write Java code which works inside the web server. So you have the web server end in Java, but you don't have the client side really in Java, because it's very memory intensive and there are lots of security problems, so people don't really use it now. And Python, which is a bit of a different language from all the others. This is what's called a scripted language. So the main thing about a scripted language is that you really use it for calling programs rather than actually writing your own programs. You just write little simple programs which call other programs and join the results together. So this is really a language if you don't want to be a hardcore techie. It's quite useful for writing little helper programs which help you do your job. So for example, if you want to fetch some data, maybe a file from the internet, and then do a little bit of processing on it and feed it into another program, that would be quite easy to do in Python. In the other languages it would take a lot more code. Python is interpreted. Generally it tends to be fairly slow compared to the other languages, but on the other hand it is quite a bit simpler. Okay, and finally a graph I found while I was getting this course ready, which shows you the popularity of various languages. This is worked out by looking at how many questions are asked on Stack Overflow, which is a very popular site for programming questions, a programming forum if you like. And on the x-axis they have the number of projects which are being worked on in that language in GitHub, which is a version control system. It's basically a system where people can upload their code as they're working on it and then update it each time they change their code. So they have a record of it. So if we have a language on here, that means there are lots of questions being asked about it, which could mean it's very popular or it could mean it's very complicated. And if we have a high number here, it means there are lots of people working on it in GitHub. So fortunately C++ is very high on both axes. It's one of the most popular in the world if you take this as an accurate metric. It's a little bit hard to see. The other ones are JavaScript, there's Java, there's Python, there's C hash, and there's C. So you can see that C++ is still pretty popular. It slacked off a while about 10 years ago, but there's a new version which revitalised the language really, so it's become a lot more popular again. So there should be plenty of opportunities in it should you wish to learn it. So that's the end of the video. I hope you've been convinced to learn C++ if it's the right thing for you. If you want to learn something else, that's fine, and I hope you're very successful with it. So thank you very much, and maybe I'll see you next time. Hello, and in this video we're going to look at the C++ family tree. Computer programming languages have been around since the 1950s really. They've undergone a very long process of evolution, and we're going to have a look in this lecture at how we arrived at C++. This may sound like a bit of a pointless history lesson, but in fact it is very relevant to understanding why C++ is the way it is today. So let's start in the beginning, and in the beginning there was machine code. So these are just binary numbers which are fed straight into the CPU and translate directly into voltages. This is a very difficult way for humans to work, dealing with lots and lots of numbers which don't mean anything or don't seem to mean anything. So after a few years someone realised this wasn't terribly good, and they had a very clever idea. They wrote a program called an assembler. So you could feed words into this and it would generate the numbers. So instead of entering the CPU instruction code that meant compare to numbers, you could enter the word CMP, which stood for compare, and then the two numbers, and that would spit out the corresponding machine code instruction for the CPU. So this is a lot easier for humans to work with. The disadvantages are it's pretty verbose. If you want to do something like, I don't know, open a file, for example, that takes quite a lot of assembly instructions. It's very low level. It's very much oriented towards thinking the way that CPUs think, and not the humans way that humans think. Well, I mean, CPUs don't really think, but you know what I mean. And the big problem is it's not supportable because the assembly language is different for every CPU, as the machine code is different as well. So if you wanted to write an assembly language program and then use it on a different computer, you basically had to rewrite the program, which is takes a lot of time. And then someone had the idea of taking this a step further. So this is still in the 1950s, and they wrote another program called a compiler. So you could enter words into that, and then it would generate assembly language. Then you could feed that into your assembler and it would generate the machine code, and then you could run your program. This is portable because you can just rig up your compiler so it generates the appropriate type of assembly language for the computer that you're working on. It's concise. You can have a single instruction in a high-level language that corresponds to several assembly language instructions. For example, you can just say open file, and that'll generate all the assembly language instructions that you need to do that. And it's getting a bit closer to thinking in terms of human concepts. So you can have sort of concepts such as opening files or reading in data or whatever, as opposed to just sort of poking around in memory and sending off instructions. So the first high-level languages were Fortran and COBOL. There were quite a lot of them in the 60s and later, and the one that we're particularly interested in for C++ is a language called C. This was developed around 1970 in Bell Labs, which is a subsidiary of the giant American telecommunications company AT&T. They were writing their own operating system at the time, which became known as Unix, and they also decided to write their own compiler. They did start off in assembler, but they wanted to be able to have it running on different computers, so that's why they went to a high-level language. C has often been described as a high-level assembler, so you can write in it as a high-level language, but there are also instructions which correspond to a single assembly or machine code instruction. So you can still have quite a lot of fine-grained control over the actual code that goes into the CPU, which is just what you want when you're writing an operating system, and you have to poke around with the hardware and make things very efficient. It is a procedural language only. That's the only paradigm it supports. It's good for low-level programming hardware because you can do all this high-level assembly language. There's a bit of a drawback though, because Unix became very widely used, and the C compiler was supplied with Unix because you had to be able to compile it on your system yourself. They didn't supply binaries in those days. So this meant you had a compiler. If you wanted something like Fortran or Pascal or some other language, you either had to buy it off someone else, which was very expensive, or else you'd have to write it yourself, which took a lot of time. So people started writing application programs in C. This was not such a good idea because the low-level features for poking around with hardware were still in there. So this tended to create very buggy programs. And also procedural language, as people wrote more and more complicated programs, procedural programs tended to get out of control, and this created a lot of unmaintainable programs. So in the late 1970s, the origins of C++ started. This was also at AT&T, but in a different department. They were actually replacing their old telephone switches with new ones which were software controlled. So a telephone switch is something that's in a telephone exchange. When you make a telephone call, it goes to the exchange and it gets sent off to another exchange and so on until it gets to the one nearest the person that you're calling. And the switches basically decide which is the next exchange that the call should be passed on to. So they wanted a software system to control these software switches. It was obviously going to be a very large and complicated program, and they didn't really fancy doing it in C. So they came up with the idea of adding things called objects or classes to C. And they brought in someone called Bjarne Stroustrup from Denmark. He had already written an object-oriented language called Simula. So the new C with classes was based on that. And gradually it developed into and took on a life its own, so it became called C++, because it's the next thing after C. There's a little geeky joke in there which you might not appreciate. But, you have to understand C++ to understand it, really. So C++ was designed to be more pleasant than C when writing large programs. So it kept all the features of being a high-level assembler, really. It's basically a superset of the C language. I mean, C has diverged very slightly since then, but you can still compile almost any C program with a C++ compiler. So here is the C++ family tree. So we start off with machine code, then we have assembly language, then we have C, which is a high-level language, and Simula is also a high-level language. And then they evolved into C++, which is another high-level language. So perhaps we should really have C++ at the same level here, but it looks a bit confusing. You can't really have the children in the same generation as the parents. So finally, let's have a quick look at the standardization of C++. C was standardized in 1989. The reason for that was there were lots of different versions of C around, and it was a real nuisance trying to get having programs that compiled with some C compilers and not with others. So they came up with a standard compiler, and every compiler had to compile with the standard, so you could be assured that your program would compile with it. C++ was rather different because AT&T had their own compiler called Cfront, and they made this available free of charge, so people could write their own C++ programs, and that was the standard. If your program compiled with Cfront, it was C++. If it didn't compile, then it wasn't C++. This is a bit unsatisfactory because AT&T kept introducing changes, and every time they changed the compiler, people's code stopped working, or they had to get a new compiler to use the new features. And also AT&T got a bit tired of being in control of the standard. It's not really what they wanted to do. So they got involved with the International Standards Organization as well, and in